This is an inductor. It consists of loops of wire wrapped around a cylinder. What would happen if I allowed current to flow from the right side to the left side? Well, let's use the right-hand rule. My fingers will be in the direction of the current. They'll wrap in this direction, and my thumb will point in the direction of the magnetic field which is created. So when current flows from the right to the left, there is a magnetic field which points from the right to the left. And that magnetic field is strongest inside the cylinder, and it is very weak outside of the cylinder. The circuit symbol of an inductor looks like this. Let's connect our inductor to a battery and a resistor. And let's put in a switch. An inductor is given the symbol L. We have our voltage source and our resistor, and this is our switch S. Now, what happens if I close the switch S? Well, if I close the switch S, current is going to flow through the inductor from right to left. But that current is going to be initially increasing. And we have a magnetic field which is pointing from right to left. But the inductor, by Lenz's law, is going to want to oppose that increase in the magnetic field. So it's going to try to create a magnetic field which points from left to right, like this. So the inductor is going to it's going to be a source of EMF which points from left to right. So I could even take that circuit, I could replace that inductor with a EMF. Let's get rid of that inductor. And really, I could replace that inductor with a source of EMF. That's called the voltage of the inductor. As the current increases, the inductor is going to have an induced EMF which points in the direction opposite to the direction of increase of the current. So an inductor opposes the increase of the current. Now, normally, if we didn't have the inductor in the circuit, what would we have? The circuit would look like this. And when we close the switch, what's going to happen? As a function of time, the current is going to increase very suddenly to a value of V over R. That's if there's no inductor in the circuit. But now, if we have an inductor in the circuit, this EMF, which is opposite to the direction of current flow, is going to reduce the amount of current which flows. So our graph of current versus time is not going to suddenly increase. It's going to slowly increase. It's going to look like this. And eventually it will reach that maximum value of V over R. We'll work out the mathematics of all this later on. Let me put the inductor back into our circuit. Let's now compare this with a circuit that has a capacitor in it. Here's our capacitor. Voltage source, the switch, our resistor, C, R, S, V. Now, what's going to happen when we first close the switch? The capacitor is going to act like a short circuit. The maximum current is going to flow, which is equal to just the V over R. But then, as time goes on, that capacitor becomes charged, and it starts to oppose the flow of current. And eventually, the capacitor is going to act like an open circuit, and no current will flow. So the graph of I versus T for a capacitor looks like this. Start off at a high value, and then it goes down to 0. And the maximum value is just V over R. So you can see how the inductor and the capacitor have opposite behaviors. The inductor limits the flow of current initially, and eventually, as you get a constant current, there's no more magnetic field, no more changes of magnetic field in the inductor, so the inductor no longer has an induced EMF, and the current reaches the maximum value and just stays constant. Whereas the capacitor allows maximum current at the beginning, and that goes to 0 as the capacitor becomes fully charged. After a long time, the maximum current, V over R, flows through the capacitor, flows through the inductor. I equals V over R. What would happen if I now took the battery out of the circuit? So I just connect it right here and remove the battery from the circuit. There, it's gone. So what's going to happen now? The current is going to start to decrease. If the current decreases, the magnetic field inside the inductor is going to start to decrease. But the inductor is going to respond, according to Lenz's law, by trying to increase that magnetic field. So if the magnetic field, in this example, we have current flowing from right to left. Fingers wrap around the direction of the current. We have a magnetic field going from right to left. So if that magnetic field starts to decrease, the inductor is going to respond by trying to increase the magnetic field. It's going to want to cause a current to flow from right to left. It wants to increase the current from right to left. So the inductor is going to act like a source of EMF in the direction of the current, just like this. So the inductor is going to try to increase that decrease in the current. But eventually, the current will decrease, and eventually it will go to 0. It will be turned into thermal energy in the resistor. So let's look at what the current versus time will look like when we take the battery out of the circuit. We will start with the high value of V over R, and then it will go to 0. Maximum value of V over R. Now, these looks very similar to the behavior of the capacitor, doesn't it? Now, you remember what the equation was for the capacitor. We had the current is I equals the maximum current of V over R times e to the negative t over tau, the time constant. We have the same equation. It's I equals V over R times e to the negative t over tau. The only difference is that the value of tau is different for an inductor and for a capacitor. For the inductor, the time constant tau equals L over R. And for the capacitor, the time constant is RC.